This is MAP4C, day 25, lesson 3.3, line of best fit. This is day 2. And we see the goal for the 3-minute review today is to draw a line of best fit to represent a scatter plot. And instead of just getting a line here and just sort of saying, about there, that line of best fit's not very good because it doesn't account for the outlier, and that one there would be too far over with the outlier, and so on. Instead, what I like to do, and this is up to you, if you can eyeball it without doing this little idea, go ahead, is I think of putting a tight loop around all of the points, and then having your line of best fit cut that in half. So somewhere around there might be a pretty good line of best fit. That looks pretty good. And over here, perhaps tight line of best fit, or tight loop around the points. Line of best fit that cuts this in half. It's kind of weird because it's sort of flat on one side and a bump up to see the outlier. Remember, we discussed if the outlier ends up being a mistaken measurement, we just exclude that and then do a line of best fit on whatever's left. Okay, and then the lesson today is more lines of best fit, but we'll see this is actually the problem day when we have problems with lines of best fit. Line of best fit day 2. So discuss some problems. See, that's what I was talking about, some problems. But we've got a grid here, and we've got some data. We want to demonstrate a relationship between the year and the global population. Years first, obviously. This is year, and this is population. What's its population? It doesn't say. I think it's population in millions, I think. Millions of people. Let's see, right now, yeah, 6 billion would be 600 or 6,000 million, which doesn't sound right, but that's billions. Okay, and this date is actually pretty weird, but when we get to start graphing the scatter plot, year goes on the bottom, population on the side. Put a little break in the graph, and what happens here is, notice this table goes up by 50s for the first few, and then it goes up by 5. So this is a little bit tricky to graph. I'm not going to graph all the points. I'm just going to graph the ones that I put a tick next to. So every 50 years. That should be enough to show a trend, even though there's a lot of data that I'm going to actually skip. So I'm going to start at maybe 1700, year 1700. That will be 1750 and 1800. This is year. 1850, 1900. There's the year 2000 and the year 2050. And notice each tick that I put has to be worth the same amount. That's why I got to worry about all this data being so close together. I can't change my scale and start going up by 5 years. That would mess things up big time. So each tick I put was 2 squares is worth 50. 50 years, 50 years, 50 years. And on the y-axis, this is population. And notice the numbers have to get all the way up to the 6,000, 6,500 or so. But they start pretty low. So I'm going to go up by each 4 squares is worth 1,000. So each square is going to be worth 250. And I'm hoping that I can have, there's 500. There's 1,500. That's 2,000 there. And here we go. 4,000. I think we might run out of room here, but we'll get by. Yeah, because we get in the 6,000, it's up, this distance again, up here somewhere. There's 6,000. This isn't going to look very good, but we're not going to have many points up there anyway. There's 6,000, which is the 6 billion mark, which is what it is right now. About. This is going to be, once I graph it, it's going to be world population. Population of Earth. Underline. All right, let's do the points. 1750 and 800. So this is 750, so it's just a little bit over that. And I'm estimating again. 1800 was almost 1,000 people. 1,000 people. 1,000 million, so a billion people almost. 1850 it was 12, 16, about there, just over that amount. And then at 1900 it was 1650. So that's 1500. That's 1750. Just underneath that. At 1900 and 1950, 2.5 billion people, just over that. Year 2000, again, I could try and fit all of these pieces of data, there's 10 pieces of data in there, all would fit in between the years 1950 and 2000, right? So I'd have 10 extra pieces of data in there, and I'm not going to do that. I'm going to get the trend without those extra pieces of data. So the last one, 2000, was just over 6,000. So 2000, just over 6,000, way up here somewhere. All right? It was 2000. Follow that up out here. And yeah, I should have maybe fixed my graph so I could fit all that in, because that is an important point, right? It's skyrocketing up there. Describe the relationship and the correlation. So the relationship is that sentence. So I start it with, as year increases, and I always read it that way, right? I always think of the independent variable increasing. Think it that way. What happens to the population? Population, well, go figure, it increases as well. So what does that mean about the type of correlation? Well, it's a positive correlation. Positive correlation. Positive correlation means as this one goes up, the other one goes up. Negative is when it goes down. Positive correlation. Okay. So it's use your line of best fit. Did it ask me to do a line of best fit? Oh, right there. I forgot to do my line of best fit. So again, I'm going to do a tight loop and use the same sort of deal on this side. Tight loop. And I can see that it's, and then tight loop back like that. And I can see my line of best fit. If I want to split this in half, my line of best fit is somewhere in the middle of these. Just kind of eyeball that, half up, half above, half below, following the trend of the data. That would be 3 below and 3 above, following the trend of the data. I might be tempted to make it a little more slanty, so it's cutting my, almost looks like a boat, purple boat shape in half. And you and I can argue about this, but maybe like that. Goes through that one, 3 below, 2 above. That's not bad. Maybe, yeah. And again, we can goof around with this for a little while. That looks okay. It doesn't ask us to calculate the line of best fit this time. That's fine. Use your line of best fit to estimate the population in 2050. Well, notice that in 2050, that's many, many years from now. But we'd have to go, okay, 2050, and then we go up to the line, right? In 1900, we just go off the line, bounce over. Now, we might have to extend our line a little bit. Okay, extend the line a little bit. Same angle, and then over. Looks okay. And so what would we say? we'd say maybe, well, it's hard to read. It goes right off the graph, but maybe 7 billion. So we could say from the graph, the population appears that it will be, that it will be 7,000 million, so 7 billion. We got another question down here. There's the key work there from the graph. What's the problem with your estimate? The problem with this is this data isn't linear at all. Like this line of best fit, look at how far away from these points were. You know, these points were way off. It should have been a curve of best fit, shouldn't it? And that's one of the problems. That's one of the problems with line of best fit. It should have been this curve. It shouldn't be a line of best fit, but a curve of best fit. And that makes sense. This estimate of 7 billion, I think right now in 2013 it's already over 7 billion. And I'm not sure about the population of the planet. We check it on the Google. Here, let's just see what we got going. Population of Earth. And what is it right now? See that? Right there. As of today, it is estimated to be 7.1 billion by the U.S. Census Bureau. That's pretty good data there. It's already higher than our estimate for 2050. So it's wrong, 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 wrong. And that's what we want to talk about. This is a misuse of regression. And there's other ways. So other possible problems with regression is that we don't have enough points. So for instance, let's say, you know, we do a little research and and we get a scatter plot and we do a, oh, that's fine. And it looks like we've got a great line of best fit, right? There's a line of best fit and it's really, really close. But then if we survey more people, the second set of people are in blue and they don't fit the trend. But our original data was on these three. We didn't have enough points, not enough people to get a good idea of the relationship. All the data are too close together. Well, it could be, if the scatter plot looks like this. Data is too close together. You know, we try and draw some sort of graph and it looks like that. Well, where are you going to put your line of best fit? I don't know, right? You go this way, that way, who knows? Could be that there's no relationship, and that happens sometimes, right? There's just no relationship between the variables. And what would the graph look like then? Well, we talked about positive correlation and negative correlation. Well, if there's no correlation, no, there could be dots just all over the place, right? Where are you going to put your line of best fit like this? It looks like stars. Is it positive correlate or negative correlation, positive correlation? Who knows? There's just no relationship. Looks something like that. There are outliers that skew the predictions. Well, that would be the sort of thing is, let's pretend we had a nice line of best fit. You know, and this might be, you know, something like this. But we got a couple people that whatever this is, you know, maybe this is hours study, and this is hours of study, and this is your test mark. And for the most part, it's a nice, even, nice little graph there. But even you get some people, and these are the annoying people who don't study very much, but they get a really, really high mark. And then your teacher thinks just because of that one person, you should study more so you get a higher mark, and it skews the results. Where most people, it's just a nice steady increase. But if we account for that outlier, we could get skewed results. And the data isn't linear. Well, this is what happened to us on our population example, right? It wasn't linear. It was, and maybe you remember what type of graph that is. Kind of looks like that, right? And we'll talk about this in a couple of chapters. This is actually an exponential model. But it doesn't have to be an exponential model. That's not linear. We can see parabolas in data. We can see all sorts of shapes in data. Okay? And we'll actually talk about these sorts of things more, and finding out equations of these curves of best fit in chapter 5. I think that's it for today. Yeah, sure is.